All right, we are starting a new module, or chapter, I should say, today on circles. So today we're going to have some terminology and some bad news. We do have proofs coming back into our assignments, but no big deal. We're used to proofs and we can handle them. All right, so some vocabulary today. First of all, two or more coplanar circles, which means they're on the same plane or say same paper or page, with the same center are called concentric circles. So they have the same center. And we can see a picture of one right there. Now, another important thing to remember is two circles are congruent if they have congruent radii. Okay, so if two circles have the same radius, then they're congruent. Then they're the same size. So on our picture here, we have some identification. So 0 on our picture refers to the center of that circle. A on our picture would be located inside the circle. Okay, so the distance from the point to the center is less than the radius. Point B here would be on the circle. The distance from O to B is the radius. And C here would be outside the circle. The distance from O to C is greater than the radius. Now, a chord of a circle is a segment joining any 2 points on the circle. So, a chord is a segment joining any 2 points on the circle. So, that would be this in this case, all right? Now, the diameter of a circle is a chord, okay, but it's a chord that passes through the center. So here, that is also a chord. Its endpoints are on the circle, but it passes through the center. All right, so the distance from the center of a circle to a chord, so this next part is kind of important that we defined. The distance from the center of a circle to a chord is the measure of the perpendicular segment from the center to the chord. So we would mark that right here. Okay, so this is perpendicular, and we'll call this D here. Okay, this would be D in our picture above. Now, if a radius, this is really important too, we use this a lot. If a radius is perpendicular to a chord, then it bisects the chord. And so on our picture above, that chord that I just marked the distance to, D, would be bisected. It would cut that chord in half right here where it intersects that chord. Now, the converse is also true. So if a radius of a circle bisects the chord that is not a diameter, then it is perpendicular to that chord. So if a radius is perpendicular to a chord, it bisects the chord. If a radius bisects the chord, then it's perpendicular. And the perpendicular bisector of a chord passes through the center of the circle. So on here, on this picture to the right over here, we have all of that, right? So we have OG here would equal the distance from the center to the chord. And we can see that it is perpendicular. It bisects that chord EF. And there we go. So moving on, let's take a look at a proof. Yes, proofs are back. So we have circle Q. We have statements, reasons. So we have circle Q, and we have PR perpendicular to ST. All right, so we have this. Okay, so when we have perpendicular, we know then it makes right angles. So we can say angle SRP and angle TRP are right angles. And that means perpendicular makes right angles. And then we know that angle SRP is congruent to angle TRP because all right angles congruent. Now, so we are going back to our congruent triangles here because what we want to prove ultimately is PS congruent to PT. And to do that, you can see they're part of the two triangles there. So if we're focusing on congruent triangles, we could say PR congruent to PR, and that's reflexive. And we'll mark that there. Now, our new theorem. Remember, if a radius is perpendicular to a chord, and Q, even though it's not QR, it's you know, if we extended QR, it would be a radius. It is starting from the center. So, actually, we don't even need that because we have the perpendicular. We can use our theorem if, well, it's still, again, radius, but it's like radius because it's starting from the center. So if we have perpendicular to a chord, it bisects the chord. So we could say SR congruent to TR because radius perpendicular to chord bisects chord. Okay, so radius, we're going to define radius to mean starting from the center. Okay, we could extend that to the circle itself, and you could see it would still it would bisect that chord at R. Okay, so number 6. So now that we have that, we have congruent triangles. So we can say triangle PSR congruent to triangle PTR by SAS. And then finally, we can say that S congruent to PT by CPCTC. So we're using our good old, we're using our congruent triangles, but we did use our new theorem that is, if a radius is perpendicular to a chord, it bisects that chord. Next, we have our circle. The radius is 13. So anytime you're given a radius, you're going to want to draw that in. So look, I'm going to draw them both in here. There we go. So those are both radii, and they're both 13. It says that the length of the chord here is 10. We want to find the distance from the chord to the center. So I'm going to draw that in here. That's going to be this. And remember, the distance is perpendicular to the chord, which means it's going to bisect it based on our theorem. So we have our distance from the center to the chord. It's going to be perpendicular. It's going to bisect it, and we end up with a right triangle. So I'm going to call that distance from the center to the chord x, and it looks like we have 5 squared plus x squared equals 13 squared. So if we solve that, this is one that we see all the time, and we get x equals 12, and that's our answer. All right, for this last one, we have that ABC is isosceles. Get it set up here. So let's write it down. We have triangle, ABC, isosceles, with AB congruent to AC, and circle P, circle Q, BC parallel to PQ. Okay, so we got these parallel. We have AB congruent to AC there. Okay, there we go. And we want to prove that circle P is congruent to circle Q. So remember, we defined two circles are congruent if they have the same radius, right? So really what we want to prove is PB congruent to QC. Oh, that looks bad. Let's do that again. QC. All right, so if we can show that those two radii are congruent, then we will have the circles congruent. So given. All right, so on here, let's see. We're going to use those parallel lines. We're going to use triangles. So let's see. The fact that those sides are congruent means these angles are congruent. So I'm going to say next, I'm going to say angle ABC congruent to angle ACB. And that's because if we have congruent sides, then we have congruent base angles. Then those would also be congruent to these because we have parallel lines. So we could say angle ABC congruent to angle APQ, and we can say angle ACB congruent to angle AQP, and that's because parallel lines corresponding angles congruent. And then what that means that angle APQ is congruent to angle QP by substitution. So initially we had the two small angles congruent, the two pink ones. Now we have the two purple ones congruent. Well, if those two base angles are congruent, that means AP is congruent to AQ. Because base angles mean sides congruent. And so we have the whole thing congruent now to each other. And then we have the pink parts congruent. So that means we can say PB is congruent to QC because congruent segments minus congruent segments equal congruent segments. And now that those are congruent, we can say circle P is congruent to circle Q because if two circles have, oh, you know what? Let's make this shorter. Congruent radii means congruent circles. Oh, that was so much better.